So we're going to talk about empirical formulas and molecular formulas. An empirical formula is the smallest ratio, the smallest whole number ratio that you can have with each of the elements in a compound. So we're going to talk about how you calculate an empirical formula. And then we're going to talk about how we can determine a molecular formula given the empirical formula. So there's a list of steps here on how to calculate an empirical formula. I think what's a little bit more useful is if we actually look at an example. So let's look at an example here. We have a compound that contains 1.71 grams of carbon and 0.287 grams of hydrogen. So the first thing that we're going to do is we're going to convert the number of grams into moles. So for carbon, we have 1.71, not 17.1. 1.71 grams of carbon, and the molar mass of carbon is 12.01 grams per mole. So grams of carbon cancels with grams of carbon, and we're left with moles of carbon. If you divide 1.71 by 12.01, you come up with 0.142 moles of carbon. Now we're going to do the same thing for hydrogen. So hydrogen has a molar mass of 1.01 grams of hydrogen. Per mole. So if we take 0.287 and we divide that by 1.01 grams, we come out with 0.284 moles of hydrogen. So then what we do is we find the smallest number of moles. Between carbon and hydrogen, carbon only has 0.142 moles, and for hydrogen we got 0.284 moles. So the number of moles of carbon is smaller, so we're going to divide both of these by the number of moles of carbon. So if we divide 0.142 moles by 0.142, that gives us 1. If we divide 0.284 by 0.142, that comes out to 2. So this means that we have 1 carbon for every 2 hydrogens. So our empirical formula would be CH2. Now we don't need to write the 1. Whenever there's only one of an element, it's just understood to be there. We don't actually write it. So we would just have CH2 here. Let's look at another example. We have a compound that is determined to contain 5.31 grams of chlorine and 8.40 grams of oxygen. So if we look at chlorine, we have 5.31 grams of chlorine. And if you look at the periodic table, the molar mass of chlorine is 35.45. So I'm going to write this all the way over to the side here, so that hopefully I don't run out of room this time. So if we divide 5.31 by 35.45, we come up with 0.150 moles of chlorine. For oxygen, we have 8.40 grams of oxygen. And the molar mass of oxygen is 16 grams per mole. So grams cancels with grams. If you divide 8.40 by 16, you should come up with 0.525 moles of oxygen. So again, the number of moles of chlorine is smaller than the number of moles of oxygen. So we're going to divide everything by the number of moles of chlorine. Since we're dividing 0.150 by 0.150, that's going to come out to 1. If we divide 0.525 by 0.150, we come out with a number that is not exactly a whole number. We come out with 3.5. Now, obviously, we cannot have 3.5 oxygens in a molecule, so we have to make that a whole number. So since this is a half, if we just double this, then that gives us a whole number. 3.5 times 2 is 7. Now if we double the oxygen, we also have to double the chlorine. So 1 times 2 gives us 2. So this compound is going to be Cl2 O7. Now let's talk about how we calculate a molecular formula. If we already have an empirical formula and we know the molar mass of the compound, we can take the molar mass of the compound and we can calculate the molar mass of the empirical formula, and then we divide the molar mass by the molar mass of the empirical formula and find out what we need to multiply the empirical formula by to get the molecular formula. Now that's kind of a long-winded way of explaining this. Let's look at an example which might help a little bit in seeing how this works. So let's say, for example, we have a compound that we've analyzed, and we found that it contained 43.64% phosphorus and 56.36% oxygen by mass. So we're going to start with phosphorus, and to make our lives easier, we're going to assume that we have 100 grams of a compound. The reason we assume that we have 100 grams of a compound is because percentage means per 100. So if we assume that we have 100 grams, the percentage just becomes the number of grams. So 43.64% phosphorus becomes 43.64 grams of phosphorus. And if you look on the periodic table, the molar mass of phosphorus is 30.97 grams. Per 1 mole of phosphorus. So if we divide 43.64 by 30.97, we come up with 1.409 moles of phosphorus. And for oxygen, we have 56.36%, which becomes 56.36 grams of oxygen. And the molar mass of oxygen is 16 grams per mole. So grams of oxygen cancels with grams of oxygen. And 56.36 grams divided by 16 gives us 3.523 moles of oxygen. So the number of moles of phosphorus is smaller, so we're going to divide this by the number of moles of phosphorus. And since we're dividing by the number of moles of phosphorus, this is going to come out to 1. And when we divide 3.523 by 1.409, we come out with 2.5. So again, we can't have half an oxygen, which means that we've got to multiply this by 2. So 1 times 2 is going to give us 2. 2.5 times 2 is going to give us 5. So that gives us an empirical formula of P2O5. That is our empirical formula. But we want to know what the molecular formula is as well. So if we calculate the molar mass of P2O5, phosphorus has a molar mass of 7 grams per mole, and there are 2 of them. And oxygen has a molar mass of 16 grams per mole, and there are 5 of them. So if we add that together, we get a molar mass of 141.94 grams per mole. So, when you're given a molar mass of 283.88 grams per mole for our compound, so what we can do is we take the molar mass of the compound, which is 283.88 grams per mole, and we divide that by the molar mass of the empirical formula of our compound. So if we divide 283.88 divided by 141.94, that comes out to 2. So that means the molar mass of our compound is twice the empirical formula. So we're going to multiply the empirical formula by 2. So we get P4O10 for our molecular formula. So let's try one more example here. We have a compound that contains 47.08 grams of carbon, 6.59% hydrogen, and 46.33% chlorine by mass. And the molar mass of the compound is 153 grams per mole. So we're going to do the same procedure here. For carbon, we have 47.08%, which we're going to say is 47.08 grams. So 47.08 divided by 12.01, that gives us and then for hydrogen, we have 6.59 grams of hydrogen per 1.01 grams of hydrogen per mole. So if we divide 6.59 by 1.01, we come out with 6.52 moles of hydrogen. And for chlorine, we have 46.33 grams of chlorine, and the molar mass is 35.45 grams of chlorine per 1 mole. So grams of chlorine cancels with grams of chlorine, and if you divide that out, we get 1.31 moles of chlorine. So in this case, chlorine has the smallest number of moles, so we're going to divide everything by the moles of chlorine. So 1.31 divided by 1.31 is 1. 3.92 divided by 1.31 comes out to 3. And 6.52 divided by 1.31 comes out to 5. So that gives us an empirical formula of C3H5Cl. That's our empirical formula. Now, I'm going to let you calculate the molar mass of that. And once you have the molar mass, what we're going to do is we have the molar mass of the compound. So we're going to take 153 grams per mole. And if you calculate the molar mass of C3H5Cl, you should come up with 76.53 grams per mole. So if we divide 153 divided by 76.53, we come out with 2. So that means we need to multiply everything in the empirical formula by 2, which means that our molecular formula is C6H10Cl2. So we're going to stop here, and we will get some more practice with this in class.